Good morning, everyone. Thank you for joining us today for the Introduction to Ammonia Refrigeration webinar. My name is Beth, and I'll be hosting today's webinar. We would like to start today with a safety moment. Safety is a core value at PGE, and we want to remind you to be safe around electricity. As you consider installing or retrofitting new equipment, please keep safety in mind. We also encourage your family, tenants, and staff to be prepared with an outage kit. You can visit our website for more safety information. We also want to thank the Energy Trust of Oregon and the Northwest Energy Efficiency Alliance for their support in co-sponsoring this series of free energy efficiency trainings that are open to all Northwest utilities and their customers. Before I introduce today's presenter, I would like to show you some tools you'll be using during the webinar this morning. To the right of your screen, you'll see several windows: the participants window at the top, the chat window, and the polling window, which will appear at the bottom of the screen at the end of the webinar. If you have any questions during the webinar today, you can submit them to me through chat. I'm the host, and the instructor will answer them at the end of the webinar. Because this will be an informal session today, if you'd like to share an example or you have a question you'd like the instructor to address immediately, please feel free to raise your hand using the raise hand icon, which you'll see at the bottom of the participants window. At the top left corner of your screen, beneath the Quick Start tab, you'll see several tools, which I will underline here in red: an annotating tool, an arrow, a marker, and a text tool. The presenter today will ask you to use these tools on specific slides during the webinar. And now I'd like to introduce today's presenter. David Wiley is Vice President of ASW Engineering Management Consultants. David is one of the founders of ASW in 1976. He has an engineering degree from Cal Poly San Luis Obispo and completed an MBA at National University, which provided him with even more tools to analyze energy efficiency investment from both a mechanical and a financial perspective. He holds college teaching credentials and has an ability to take sophisticated engineering concepts and relate them in a way you can understand. Several of his articles have been published in trade magazines, and he has written a book titled New Refrigerants for Air Conditioning and Refrigeration Systems. David recently served as committee chair for ASHRAE Custom Engineered Refrigeration Systems Research. And now I would like to turn the presentation over to David. David?
Thank you, Beth, and glad those that are here to go over some things in industrial refrigeration. So I'm going to get my pointer going here. There we go. All right, see the little bouncing ball. So that's what we get to use as a pointer today. So we have an hour full of some interesting information, and it is focused on 3 or 4 areas where efficiency is discovered in refrigeration systems, and I think you'll see where this is successfully being achieved. Looking at the slide we've got here now in front of you, should be able to see a couple of the areas that we've included. A little discussion of a recently constructed refrigerated warehouse, and it actually achieved a LEED rating, which is a little unusual for industrial process, but they were particularly focused on that. The second bullet here, concepts of floating head and suction pressure. Not a necessarily new idea, but something that's a little tricky to accomplish and has substantial energy savings. And then the last bullet here we have is the potential savings utilizing a variable frequency drive on a screw compressor. So we'll take a look at what some of the results that are achieved on both low and medium temperature applications. So hope you find that interesting as we proceed here. There we go. So here's the warehouse. We're titling the super efficient refrigerated warehouse, and I think it deserves a rating like that because it's about 60% more efficient than a typical warehouse. From the outside, the bottom left picture here might look like any other warehouse, a little more interesting on the outside. It's about 135,000 square feet, and the energy savings that have been attributed to this special design is about 3.4 million kilowatt hours. One of the things you can tell by the inside, not so much from the outside, but the very tall racking equipment here. Part of the design is to have an aspect ratio that gives more storage per square foot, so there's less surface area to lose or have any heat gain through. Generally fitting about 4 times the amount of product into this space for the given square footage. It's highly mechanized. You can see the retrieval lifts here. Those are manually operated. The operator would sit in the booth here, but automated to the extent of going to a particular location to either retrieve or place a product on the racks, which are about 50 feet high, as you can see inside here. Also, there's about 80% energy savings in the lighting. So as long as we're on the slide right here, these are LED lights that are controlled with occupancy sensors, so that when someone is not particularly moving in one of the aisle areas, then this lighting would go off. And a nice aspect of LED is their ability to come on almost instantaneously, as compared to the traditional high-intensity discharge lighting, normally left on continuously because of the 10 or 15 minutes it takes for lighting to come on. So interesting building in itself. On the next slide, here's a diagram of the refrigeration system. They're using the things we're going to talk about today. It's all standard equipment. We have high-efficient compressors, variable speed on those, and variable index, or VI. Floating suction pressure, we have efficient condensing, floating head pressure, variable frequency drives on the condensers, evap condensers, and we also have efficient evaporators. Well, I'm going to go back a slide here. Next slide forward. Okay, we'll take a look at those evaporators are in penthouses. Above it here is the variable speed compressor itself, and variable frequency drive inside this panel right here. Compressor. There's also a slide valve. You can see that in that diagram there. Here's the back of the house, the evap condensers, and there is a refrigerant recovery tank here in case there's ever an accidental release of ammonia. Can be placed in that tank. Here's looking at the roof. These penthouses right here are where the evaporators are. There's 4 of them. So then accessible through a standard door here. So to provide maintenance on the evaporators, it's access through the roof. This is in lieu of hanging the equipment inside or on the walls. And of course you can see the photovoltaic panels. That's about 1.1 megawatt, and it supplies roughly 70% of the power for the site just from those panels. So interesting, can be done, and this was all achieved in a cost-effective fashion. So when assessing refrigerated warehouses, this is an example of well, where we've come. And notice in this graph here, we've got annual kilowatt hours along the left, and then along the bottom here, the total kilowatt hours and then those kilowatt hours attributed to evaporator fans, low temp compressors, the lighting, medium temp compressors, the evap condensers, and then a little bit of office equipment or air conditioning for office space at the warehouse. And then on the right, notice we've got 4 different types of facilities. These would all be the same size, but in 1985, the vintage type system we would see then and earlier than that, sort of a baseline for comparison reasons here. Typical standard practice in 2005. Many of the efficiency measures that we're going to cover today were not considered standard practice at that time, not necessarily. Let's look at 2008 energy efficient. So let's have more efficient refrigeration, increase insulation around the building, variable frequency drives on the evaporator fans, floating head pressure, variable speed drives on the condensers, and we can see the significant reduction in energy use here. And then in 2012, we're saying the most efficient, similar to the warehouse that we were just looking at. So we go a little bit further with state-of-the-art systems, adding LEDs, lower condensing temperature design, so we're going to increase the surface area of the condenser, variable frequency drives on the compressors, floating suction pressure, as well as the floating head pressure, so we continue to get savings. So typical 1985 at 3.5 million kilowatt hours, achieving the same amount of product cooling for just over 1 million kilowatt hours. So representing the reductions in kilowatt hours, you can see in the particular systems where some of the big steps are for energy savings here. And notice in evaporator fans, the use of variable frequency drives represents a pretty big step in that one here. Low temperature compressors is the use of variable speed on the compressors. Here's lighting going from HID to fluorescent and then to LED with occupancy sensors. Medium compressors, medium temperature, applying the variable speed drives. Condenser fans, even though they don't use that much power, this is adding variable speed to those. So this would be the goal then, the more efficient approach that we're using today, and the rest of our time here is going to be spent looking at how that might be achieved in the type of equipment that we use to do that. Okay, so refrigeration systems typically fall into one of these categories, suggesting that between 2 and 75 horsepower quite often is catalog type equipment, sometimes just known as single systems, and we have several single systems, but this implies one compressor, one condenser, and one evaporator. I'm going to switch to the next slide for a second. Here we go. Single systems. Typically, the refrigerated equipment inside the refrigerated space here, but here we've got a piece of catalog equipment. Inside here is the compressor. Here's the condenser, refrigerant lines, and notice we've got 3 separate single systems here. When we get to the intermediate package sizes, generally from 50 to say 500 horsepower, usually a assembly of equipment, a contractor would put that together possibly on a skid and then ship it to the site as a single piece of equipment. And then of course getting over 300 horsepower, usually this equipment is shipped to the site and assembled at the site, and these systems get up into thousands of horsepower. We can take a look here at intermediate packages. There's some advantages to the intermediate package over, say, the single the single systems. It's generally can have more efficiency built into it, often using an evaporative condenser or using water evaporating to condense the refrigerant. Disadvantages might be it takes a little more operator skill. These systems here, as you can see, the compressors, electrical equipment, all skid mounted, makes it difficult to expand the system. Once it's installed, to add more to it, not easily done. And generally, not using ammonia as a refrigerant. We can see here R22 today might be using an alternative like R422D or 507, some other halocarbon refrigerant. Although these packages could be ammonia, they typically wouldn't be. Although with the advent of a microchannel condenser, we may see both ammonia showing up in package systems like this. Wouldn't be surprised to see that soon because we have a single component microchannel all aluminum condenser or intermediate packages. And then here's a picture of a large built-up engine room where we have individual compressors. You can see the size of that really prevents skid mounting. There's numerous vessels for holding the refrigerant, typically being ammonia, although carbon dioxide is coming into play in some of these systems. And even here we can see different size compressors for staging, and that would be based on what level of product cooling or storage that we might have. Now, these larger built-up systems usually are the most efficient or have the opportunity to become that way. There's unlimited tonnage, life of the equipment. Some of this equipment gets to be 50, 60 years old, still operating, can be rebuilt. So the good news is efficiency and flexibility. Of course, the long construction cycle is something that makes this a little more difficult. These aren't generally ordered out of the catalog. They have to be designed. This is going to have our highest first cost. Our maintenance is at a higher skill level, and generally in these systems using ammonia. So our three categories of sizes: single systems, intermediate packages, and large engine rooms. So let's see. I think everyone's probably gotten online now that's going to be there. How about if y'all grab your arrow and you can click on that and come down here and place your name next to the type of system that you have. So here we go. I'm trying to get my arrow to work. There we go. Aaron shows up. Aslan, yes, okay. So we got a couple there. Everyone finds your arrow. Okay, we're going to have a couple other exercises like this, so hopefully you can find it. There's a check mark. That's good. Sort of intermediate sizes. Some larger engine rooms. Very good. Okay, there's Holly. I'll put mine down there right next to the 300 horsepower or larger. Okay, yeah, we're all starting to show up there as we thought. Very good. Okay. Well, let's carry on then. So thank you for that exercise. So here's what we might find in the large engine room. I want to point out a couple things on this compressor in particular. This is the electric motor, the variable frequency drive inside of this cabinet right here. Here's where the screw rotors are. And then of particular interest, this is the slide valve. Slide valve is utilized to allow the refrigerant that's entering the compressor to be released back to the suction, which is a means of unloading this compressor. Many times these motors are hundreds of horsepower, and we don't want to be turning them on and off repeatedly like a home air conditioner, so they remain rotating. But at the same time, if we don't need the full refrigerating effect, we'll actually adjust this slide valve, which allows the refrigerant to be drawn back into the suction of the compressor. The larger vessel down on the bottom down here is where the oil can separate. The rotors inside the compressor do need lubrication. That's injected right in with the refrigerant, separated out, and then the vapor is pulled from there and discharged to the condenser. This is where the big energy user in these refrigerated systems. So here we have a artist rendering of a typical system with compressor depicted here. Hot gas is discharged to the condenser. Here we're showing what might be called an air-cooled condenser. We're just using ambient air to blow that over the hot refrigerant gas and discharge the heat. The refrigerant vapor gives off enough heat to the point where it begins to phase change into a liquid. If you could see inside these tubes right along the way here, we'd have liquid forming, more liquid. At some point here, it might seal off with liquid, and then the liquid continues to cool down towards the ambient, and at this point we have high pressure liquid refrigerant. Often we call this the high side or high temperature side. The refrigerant under pressure then would be metered through some type of an orifice. Here it says an expansion valve. Sometimes that's a needle valve, and it would fluctuate. There are various types of valves here, but the primary purpose of this valve is to regulate the flow of the liquid refrigerant at the rate that would match the cooling effect that we want here in the evaporator. As a pressure reduction occurs, and it does occur because the compressor is increasing the pressure leaving the compressor, it's also reducing the pressure or pulling on this side of the system. We often think of a compressor as pushing, but it's also doing an equivalent amount of work on pulling vapor out of the evaporator. So the high pressure liquid would be introduced to the low pressure side, and as we have air from the refrigerated space come in contact with the heat exchanger, the evaporator, that liquid refrigerant begins to phase change to a vapor, absorbing heat at a temperature that we want. And that temperature can be controlled by adjusting the pressure in this evaporator. The lower the pressure, the lower the temperature. So we may want 20 degrees in this evaporator. Then for a given refrigerant, say ammonia, we would adjust the pressure that this particular compressor would operate at, which would be around 4 pounds per square inch gauge. If we wanted to go to minus 20 degrees, that's very attainable, say in a evaporator and using ammonia, but we would go to a lower pressure. We'd actually go into a vacuum, about 34 inches of mercury, and that's a way of measuring vacuums by how far a manometer would pull mercury down. And in this case, if we wanted minus 20 degrees, a vacuum would be necessary. A bit of a disadvantage of ammonia is that, when we get below about 20 degrees, we do have to operate the low side in a vacuum, which means if there are any leaks, that air is actually drawn into the system. Of course, air does not work well as a refrigerant. That air usually ends up trapped in the condenser, we need some way to vent that out. It's known as purge. If we stay above 20 degrees, then of course we get to stay above positive pressure, and if there's any leaks, then the refrigerant leaks to the outside, not so much the air drawn in. So we can control the temperature and the refrigerating effect by metering the quantity of refrigerant going through this valve. This is why the system needs to adjust on a very hot day or when there's high heat gain. So the product could be warm, the process could be underway. A lot of heat being absorbed by the evaporator, of course, uses a lot of the refrigerant in that phase change. So more refrigerant is metered to the evaporator. If the heat gain is not at peak or reduced, then this metering device would reduce the flow of refrigerant, and then we need some way of backing off on the compressor. So sometimes we have multiple compressors or variable speed or slide valve modulating the flow of refrigerant, because what we want is the compressor to match the flow of refrigerant as the metering device. So if half of the refrigerant is only needed, then only half of the compression is needed. And the controls would maintain that to keep the space temperature and then modulate the flow of refrigerant. And as mentioned earlier, we can't have these large compressors turning on and off repeatedly. It would put strain on the motor, and starting torque and stress on the motor and compressor would be shortening the life. So we would want some way of modulating. Okay, so there's our basic system here. So whether we're at minus 20 degrees or plus 20 degrees, so with a low temperature system, we might be at minus 20 or lower. Minus 40 is attainable with ammonia. If we want to go below minus 40, we would go to a different refrigerant, and carbon dioxide might be one of those. So from the lowest temperature, here we say minus 20, to our condensing temperature, say 95 degrees outside. This is known as lift. So from the lowest to the highest temperature. On a really hot ambient day, we may be condensing at near 100 degrees. And of course, we're trying to maintain minus 20 because of that extreme day. But notice here, we have a milder day or winter time. It could be, below 50 degrees ambient. We could condense somewhere around 70, 75 degrees. And we may not always need minus 20 degrees. Maybe minus 15 would be sufficient to maintain product temperature. So here's the idea of floating the head pressure down, or the discharge pressure when the ambient allows us to do that, and possibly floating the suction pressure up. We don't need to have our refrigerant as low of a pressure to attain the proper storage temperature. That's known floating suction. So if I go back a slide here, we're saying, okay, we need a particular temperature here to do the process, but if that lowest temperature isn't always needed, we can adjust this temperature up and still get the job done, known as floating suction. And then, of course, on this side of the system, where we're rejecting the heat, if the ambient conditions, be it the humidity or the temperature, are low, we can get the refrigerant condensed at lower temperature and pressure. That's going to give us an efficiency improvement in the area of about 2% per degree. So for every degree we can condense at a lower temperature, saving 2% at the compressor, and for every degree we can get the cooling done at a higher temperature, that has also about a 2% savings per degree. So we call that floating the head or floating the suction. And on the higher temperature systems, let's say we're maintaining 20-degree evaporator, we still can float that where possible, and floating the head pressure when Mother Nature allows us to do that. So these are two common things. They do require controls, and in some cases, a commitment to get those to work right. Here's a example of what we call fixed head pressure. Of course, if we're not using the controls or attempting to attain these savings, we've got Mother Nature out here at 50 degrees, the ambient, and this could either be wet bulb or dry bulb, depending on whether you have evaporative condensing or not, but the idea roughly the same, that ambient is low, say in the winter time here, and we would still maintain a condensing temperature, say, of 85 degrees. Sometimes this is done for, well, compressor design, oil, separation issues. There are reasons why fixed head pressure is designed into the system. Notice here we get a hot day in the middle of summer and ambient goes up. Of course, our condensing temperature will just rise with the heat of the day. But out here in the winter time, when we could be condensing maybe down here about 10 degrees or so above the ambient, we're just not taking advantage of it. Floating head pressure is indicating that we're adjusting the set point so that when we're at an ambient of around 50, then maybe we're condensing at 60, 65, and taking advantage of that lower ambient conditions. Of course, on a hot day, all the fans in the condenser are probably running full speed. We're doing the best we can to keep up with the heat gain. Floating head pressure control diagram here, saying that we measure the ambient conditions, measure the refrigerant pressure, and then adjust the speed of this fan to attain a set point. Notice here the variable speed drive or variable frequency drive or permanent magnet DC motor, whatever technique we use here to adjust the speed of this fan to get to a set point that's attainable, and of course the ambient is a moving target throughout the day and throughout the year. We might say, why not have this control system? Why not have floating head pressure control? And sometimes this is the reason. This is a variable speed condenser control panel. You can see the variable frequency drives here. These are for the condenser fans. There's other controls, microprocessor controller, and of course this takes extra care. Some feel that these added controls are more complex than they want to deal with. However, we're seeing savings in the neighborhood of 15 or 20% on an annual basis. Other reasons why floating head pressure is sometimes not pursued is flash gas. Sometimes as the liquid from the condenser is heading to the metering device, if we lower the pressure, little vapor bubbles form in the liquid line here, which results in erratic operation of the metering device. So that might be a concern. Liquid feed problems. Also, I guess our picture's depicting a reciprocating compressor here. With a screw compressor, the velocity needed on the discharge here to separate the oil from the refrigerant is a function of an oil separator design. And lower first cost oil separators generally do not provide the capacity to do adequate oil separation at lower pressures. So we end up with a carryover of oil, and that may be an inhibiting aspect of attaining floating head pressure. Also, a means of defrosting the evaporator coil here may require using hot gas that is just routed over to melt the ice off the evaporator. Of course, that hotter gas may need to be at a higher temperature during defrost, which is intermittent and generally infrequent. So at times the controls may have to go back to a fixed head pressure and get the defrost done and then go back to floating head pressure. So these are all really concerns of floating head pressure. They're valid concerns, but generally the design of the system and operation and control sequence are the ways to overcome those concerns. And of course, attaining the energy savings is the ultimate goal here. Here's a day or 2 days in the life of floating head pressure. And what we've got is the ambient temperature, the bottom blue line here. And then the red line is the condensing temperature. So if we're starting at nighttime through the heat of the day, and then nighttime again, and here's the second day. We just want to portray how this might control. So if the ambient, say, is down at 50 degrees, and we may have a cutoff or a low temperature a low temperature control set point of, say, 70 degrees, and quite often that's due to oil separation. We might be able to get down to 60 degrees, but because of our equipment, maybe we're prohibited from that. So we would just run the variable speed fan to attain an actual condensing temperature of 70, even though our ambient might be down here at 50. Now notice as the day comes along and we get up to a 60-degree ambient, now we've got about a 10-degree difference between condensing and ambient, and then we're just following along here. So the set point would go right on up with the ambient. Here's the peak of the day, so 71-degree day, 81-degree condensing, and then we would have our set point continue to adjust to the low limit. Notice the next day here, we're getting a warmer day. The ambient's maybe going up to close to 90 degrees, our set point, and notice all along here it's about a 10-degree temperature difference. Then right here the ambient is 80 degrees, the condensing temperature is 90, and notice it says high limit. And when the control system detects the high limit, this just implies that we're going to have the fans running at full speed. If we're on variable frequency drives, and notice in the panel here, our frequency drives would then be detecting the conditions where full speed in order to maintain condensing temperature as best we can. And then as ambient drops off, then we just follow it again. So this shows really the day in the life of, or 2 days in the life of a variable set point control with floating head pressure. So here, let's see. If the ambient temperature is up here at around, let's say 85, 86 degrees, and all fans are going full speed, how about you take your arrow, everyone grab your arrow and point it somewhere on this chart where the likely condensing temperature would be at the peak of the second day here. So it says high limit, but that's not necessarily the temperature we'd be condensing at. The condensing temperature is going to be ambient plus whatever the condenser can do. So let's see, grab your arrow. Okay, let's see, I see Renee is, well, kind of, there we go. Yeah, all right, Mike. Yes, okay, so the idea being we're going to be condensing, at some temperature up here because we're doing the best we can. We're full speed ahead, and really at this point the control would be just to reject the maximum heat at full fan speed. Okay, so good. Thanks for participating there. Okay, now let's take a look at the floating suction. Notice there's not as much opportunity here. Of course, Mother Nature outside is fluctuating a lot through the seasons and through the day. Over here, we have a requirement to maintain the product, but we always don't have to be at the coldest temperature. So, here we're implying a few degrees of floating suction. Of course, a few degrees is several percents of savings, so we can achieve this and desire to have the controls and able to do that. So, back to our flow diagram here, and we're on this side of the system where we're adjusting the evaporator temperature and raising the pressure where possible to get the available energy savings. Here's a diagram of an evaporator where we have refrigerant entering the heat exchanger right here. The fans are drawing air from the space, cooling the air and discharging it over the product or through the process. Here we wanted to portray there's two areas of savings. One is the fan power itself. Inside here, and these fans sometimes range from a fractional horsepower to several horsepower, some of the large ones as much as 10 horsepower. And of course, if you had 3 10-horsepower fans, that's quite a bit of horsepower, and of course, all of that horsepower turns into heat, which would add the BTUs to the space. And we can avoid the use of that heat or use of those fans at high speed if the product temperature is maintained. Notice on this variable speed, this is the proverbial fan law that says if we adjust the speed of a fan, then the power has this exponential relationship, say 50% fan speed, 12% of the power. Of course, this is some of the savings in that when we have these fans on variable speed, that the heat of those fans is not added to the space, which also has a resultant savings at the compressor. And that's part of the desire here. The other part is the resetting of the temperature, of the suction temperature. So variable speed evaporator control panel looks very similar to the condenser because they're basically the same type of control panel. And here's a day in the life of a floating suction pressure. So take a look here in a typical 24-hour period. And let's start from the bottom up. The very bottom line here is this is a freezer temperature, so notice we're maintaining about -5 degrees. The next line up here is our amount of float that we're achieving, so we'll get back to that in a second. This line here is our suction pressure. And notice these little jagged lines here are the defrost cycle that's taking place every few hours. And then the top line here is the evaporator fan speed, denoted by the percent speed here. Over here we have pressure and temperature. And along the bottom, time, so middle of the morning, middle of the day here, and then back to another day. So we can see the processes. The temperature in the space here is going above the set point. Notice that we're dropping the suction pressure and the variable speed is down at its lowest set point, and 70% selected here because that was enough speed reduction to achieve savings at the fan, yet still have adequate throw from the fan over the product. Now, as the day is coming, day is progressing through here, we can see the float in temperature was really, well, here's 0 degrees, so we're floating the temperature up a little bit as the temperature is lower in the space. Then we go up with the float. The temperature goes a little bit above the set point, so reduce the float. So our float is going up and down, and notice it's about a couple of degrees throughout the day. Then notice here the temperature in this space goes above the set point, so the float returns to 0, and we're still above the set point, so the fan begins to speed up. This may be at a time when a product or something arrives to the warehouse, and of course there's heat to be removed out of that. So the suction pressure, notice, is lower here. Fan speeds up to the highest speed. We're not getting any float out of it. But then notice after the temperature returns back to it's really below its set point, we slow the fan down, and then we start floating the suction pressure. So throughout the day, you can see we're getting an average of 1 or 2 degrees of float, and that could be 2 to 4% energy savings. And we're getting, of course, fairly continuous energy savings on the fan. So there's an example of floating head pressure and floating suction pressure. And then here's a thought about that evaporator itself. And we know not all evaporators are created equal. Evaporators can be denoted as their specific efficiency in terms of BTUs of heat that they would absorb per fan watt. And notice here what we'll consider high efficiency evaporators absorbing 50 to 70 BTUs per fan watt. And here's our least efficient evaporators, only absorbing maybe 15 to 20 BTUs. As a general rule, anything above 30 to 40 would be considered efficient evaporators, and all these down here would be less efficient. This is a function of tube and fin spacing, motor efficiency, and I think there's about 400 or so evaporators depicted here for both medium and low temperature. And of course, medium temp here and low temp, these would be considered not so efficient. So do your homework when you actually consider your evaporators. And the last thought here that we would like to show is the impact of having variable speed on the compressor. Of course, we still may use the slide valve in conjunction with variable speed. And the slide valve here allowing gas to be returned to the suction. So here we see the slide valve actually actuating, and some of the refrigerant vapor is drawn from out of the rotors before it's compressed and allowed to come right back to the suction again. So we can adjust this slide valve to get any quantity of refrigerant to be compressed through the rotors. Now, the rotor is still turning at a fixed speed, would still have the level of friction, but we just wouldn't have as much compressing. The idea of variable speed then would be to leave the slide valve disengaged and just change the speed of the rotors, and our benefit there is through reduced friction at lower speeds. Here's an example of a typical energy use at different slide valve positions. So, for example, if we're at 50% load and we're at minus 40 degrees, a typical compressor might use about 70% of the power to deliver 50% of the refrigerant flow. At the same time, if we're at plus 40 degrees, notice the impact of that isn't nearly as much as it is at low temperature. So we do find a more interesting opportunity energy-wise at lower temperatures. Notice here's some data from a variable speed compressor and a slide valve. So notice at the bottom here we have a fixed speed with slide valve. That's portrayed by this curve. And over here we're looking at pounds of refrigerant per kilowatt, or quantity of refrigeration per kilowatt. So the higher the number here, the more compression we're getting per kilowatt. And then if we use that same compressor on variable speed, our efficiency gain is then portrayed by this curve on the bottom here that's showing improved efficiency of pumping the refrigerant with the compressor. So notice that 50% of the mass flow or refrigerant flow, we're seeing about a 12-15% savings. And if we get down here, say at 20% load, we're seeing in the neighborhood of 30% savings as compared to slide valve. So if any significant time is spent unloaded, below, say, 70% load, the variable speed renders these very interesting savings. Here's another slide with portraying the low temperature applications. So here we're using ammonia as a refrigerant, minus 35 degrees. Here's the slide valve, and it's the impact on efficiency, and then here's the variable speed. And notice the variable speed down to about 50% sustains a fairly even efficiency, where the slide valve has a degradation of efficiency, and at some point here we're seeing as much as 50% energy savings. Very interesting, especially where we have significant time at part load. Okay, well, I think that's about all we're going to squeeze in from the presentation. We have a few minutes left over here for some questions, so I think back to you, Beth, and we'll see if anyone had any comments or questions.
Thank you, David. And we want to remind you of upcoming webinars and seminars before we proceed to the question and answer portion of the webinar. Here on your screen, you'll see several, Intro to Solar next week and Efficient Lighting and Controls in May. In May, we also have 3 seminars which David will be teaching live in Wilsonville. So if you'd like to meet David and get a chance to learn from him in a classroom setting, that would be great. We have Owning and Operating Efficient Motors, Variable Frequency Drives, and Air Handling Systems in late May. Before question and answer, I'd like to remind everyone you can still submit questions to me through chat. Within a few days, we'll send you a follow-up email with a recording of the session and the PDF of the materials. And real briefly here, I'd like to draw your attention to our poll, our feedback survey, which just opened on the bottom right-hand corner of your screen. We really value your feedback, and we do use it to improve future webinars, so please take a moment to fill that out. And now for the question and answer. Our first question is one I may actually need help from the questioner to ask. But basically, David, it is, are savings 2% degree for evaporator plus 2% for condensing side, for a total of 4% per degree for both floating head and suction?
Yes, I think we would consider those as additive. In other words, for every degree we can float the head pressure down, we're roughly saving 2% at the compressor. And in addition, for every degree we can float the suction pressure up, we get the additional 2%. So let's say we float the head pressure down 1 degree and raise the suction pressure 1 degree, we could achieve, say, 4% energy savings. Those are additive. It's a result of changing the compression ratio across the compressor. So yes, they both can be done simultaneously.
Great, that's terrific. And next question we have is, can all the compressors have VFDs? And could you address the rationale for all compressors having VFDs versus only 1 or 2?
Yeah, so a good question, and of course, too much technology has its penalties and costs as well. So generally, in refrigerated systems, we have either 1 or multiple temperatures. So at a given temperature lineup, quite often all the benefits are attained with just 1 variable speed drive on 1 of the compressors. And then as that compressor gets up to full speed, you turn on a fixed speed compressor and then use the variable speed compressor for what we might call trim, or to adjust the load on an ongoing basis. Now, some like having variable speed on more than 1 compressor in case there's maintenance needed on the variable speed drive. That's a backup position, but generally all the savings can be attained, for the most part, by having variable speed just on 1 compressor at 1 suction group or 1 temperature group.
Terrific. Thanks, David. And I think we probably have time for 2 more questions here. The next question we have is, How important is a central control system in an efficient facility as opposed to using local controls on compressors?
Yeah. So central control is generally a desired operating set of tools to facilitate observation and control adjustment. However, at the same time, most of these savings can be achieved with local controls, either analog controls or a programmable logic controller at the compressor or at the evaporative condenser or evaporators within the facility. So it can be attained all the way from what we'll say, analog controls, which in some cases could be even simple controls that we would have from 20, 30 years ago. Individual programmable logic controllers, and sometimes there's many of those within the facility, but controlling in a local loop scenario, and then ultimately having a network of either those controls or a centralized energy management system. And most facilities are kind of in the evolution of moving from the analog controls to a digital control system. And those are nice to have, state-of-the-art, of course, but most of what we talked about today can be attained with just the local controls.
Terrific. Thanks, David. Our next question is, what are the biggest issues with floating? Do they need regular commissioning, and how do you commission?
Well, of course, if we're floating head pressure, then that does require measuring the ambient in an accurate way. So that would be one of the primary controls to calibrate would be the measurement of the ambient conditions. Dry bulb temperature, if it's just air-cooled, which is not very common with our larger systems, but with the smaller systems, the ambient dry bulb fairly easy, and we do have higher quality sensors that maintain calibration. But when it comes to measuring the wet bulb temperature or some means of knowing the ambient humidity level, these are the sensors that need a more regular calibration. They range in cost from $50 for a humidity sensor to several $100s for chilled mirror hydrometers and other more accurate sensing elements. And it does need regular quarterly calibration. We do rely on that sensor substantially. Of course, there's huge energy savings involved with it. And then also other set points, variable speed drive output signals, motor speed controls, low temperature set point, high temperature set point. So knowing the set points, some of the times operators get in there and have difference of opinions, and they'll adjust set points or bypass the control strategy. Maybe it gets bypassed for a maintenance procedure and then not placed back into automatic. So regular verification that the system is working is desirable, and that's something to keep an eye on in order to attain these savings that are available.
Great, David. We have time for one more question, and then we're going to sign off. How do you decide on temperature set point?
Well, okay, so there's two set points that we've been looking at today. The condensing set point, and that's a function of the surface area of the heat exchanger for the condenser, or we might say its approach temperature, or the temperature by which it approaches the ambient, which could be either the dry bulb or the wet bulb. Very commonly, an industrial system would say have a 10-degree approach, which means the condenser is capable in terms of heat transfer to get within 10 degrees of the ambient, either dry bulb or let's say the wet bulb. So knowing the equipment, basically its design characteristics, which could be attained from catalog or through empirical measurement. In other words, you run the system and take these temperatures and learn what your particular equipment can do on a given day. It's a little trickier than getting into a simple answer here, because as the ambient wet bulb goes down, so does the ability to evaporate water into the air and get the cooling effect. So it's a bit of a strategy to have a set point that's adjusted based on the approach at the condenser's design and load conditions. And then, of course, on the evaporator side, the set point is usually determined by taking a sample of the product temperature, or having a sensor embedded in particular spots of the warehouse, usually near the door somewhere, to know what your lowest acceptable temperature would be. And so that would be usually a sensor embedded in some rock salt or something that's similar to the mass of the product that you're storing. So yeah, the ambient one is a trickier one, and that is going to be determined by your system design characteristics. Okay, Beth,
Great.
I guess that was our last question, so
Yeah.
thank you.
Thank you, David, and thank you all for joining us today. We'll stay online for a while in case any of you would like to ask any additional questions, but thank you again, and we hope to see you at a future webinar or seminar. Thank you.